All right. I'm going to go ahead and get started now. How's everybody doing today? Enjoying your week so far? Always. Probably take the hat off because it's not all that cold in here. So today we're going to finish up with our discussion on binaries, which is not going to take very long. I'm going to try to do that fast because I want to get to the hard stuff. How'd you guys feel about that reading last night? Boo. It's long and it's heavy. The whole chapter is super long. Yeah, you'll note I broke the chapter up over a bunch of readings, right? So this stuff is, so we've gotten to the hard stuff. So this stuff is as challenging as anything else that we're going to do. Probably, unless we do cosmology. Cosmology is weird as hell. So if we get there, that's also challenging. But that's differently challenging. This is challenging because there's just a whole bunch of stuff they throw at you. And they're all kind of spatially related and three-dimensional. So I'm going to talk about binaries. Actually, let me jot down what I'm going to talk about so that I stay on task. Let's see. Does anybody not get their test? No. Okay. Let's see. Let's hand out tests real fast. So. Okay, so I'm not going to spend a ton of time on binaries. So, that's Kepler's law. And Kepler said, you're Tyler, right? And Kepler said, here's your test. I'm just going to wander around randomly because they're not in any kind of order. Thank you. Casey. Is Casey here? Andrew at the front. Tyson. Yours. I just had it. So yours I had to print, Tracy. That's for you. Is this you? Oh, this. You just get shoot chicken scratch, not the actual test. Because I didn't bother printing it because I don't have all that much to say. Mostly, here's your points. So, okay. Now we finished that. Hey, sweet. That was everybody but Casey. Is anybody going to see Casey sooner than I am? No? Okay, I'll hang to it. Okay. What am I doing? Oh, I took out the wrong folder, which had the wrong notes in it. Okay. So we're going to do mass from visual binaries. And then we're going to do mass from spectroscopic binaries. And then we're going to talk about eclipsing binaries. And we're going to talk about how to get a temperature ratio out of those. And then I'm going to say, okay, so the chapter's kind of weird. The chapter 9.1 just throws a bunch of equations that are all really the same equation and just has all these equations. The reason for that is we've got this very complicated radiation field that we need to talk about. And sometimes we need to take various averages of this one radiation field. So I'm not going to spend a lot of time on that. I'm just going to briefly talk about kind of the parameter space that we're working in. So we'll talk about radiation, and then we'll talk about temperatures, and then we'll actually get to opacity. And we'll talk about what opacity is, and really opacity is about cross sections. So we'll talk about cross-section, and then we'll talk about opacity, and then we'll talk about how opacity affects the light. Okay, binaries real fast. I'm going to see how quick I can do this. Mostly you're going to learn this stuff when you sit down and put your hands on it in the homework. Point the camera at the right board. Okay, so we talked about several different types of binaries, which I expect you'll be able to be familiar with that list of binaries and what different types of binaries mean. Because the differences between different types of binaries is really how close they are in separation, in physical separation, how close they are in luminosity. Because if one of them is way brighter than the other, then you can't see the smaller one. If they're too close, you can't see that there's two stars there. So sometimes you can see the motion and an angle. So there's three things that we use to classify a binary. It's how close they are in space, how close they are in luminosity, and the angle at which they're rotating. So if the plane is pointing at you, then you can see the velocity and you can see the binary easier. If the plane is perpendicular to you, unless it's a visual binary, you can't see it. So let's say that I can see them both. So what happens, I've got two stars. They're both on elliptic orbits centering around the center of mass. So the center of mass is at one of the foci of both ellipses. And they both have semi-major axes, A1 and A2. So what I'm going to see is I'm going to see two stars orbiting each other, and they're orbiting this one point in space. If the stars are equal mass, then that point is halfway between them, and it's just a point in space. If the stars are way different in mass, then the point that they're orbiting might be inside one of the points, but they're still both orbiting one point. Now, when we go through this, so when we did this math, we have this one problem that has an R1 and an R2, and we broke it into dealing with just R, which is R1 minus R2. And we dealt with this reduced mass system. And we had this semi-major axis A. But this is for the reduced mass. If I want to think about both things, then the reduced mass A is equal to A1 plus A2, where A1 is the actual semi-major axis of the first planet, and A2 is the actual semi-major axis of the second planet. So these are related. So now we go up here to Kepler's third law, and I can say that, let's solve that for the mass. So the mass goes on one side and the period goes on the other side, and I'm left with M1 plus M2 equals, again, 4 pi squared over G. Oh man, I didn't plan ahead well enough where I was going to put those things. A1 plus A2 squared over the period, cubed, over the period squared. So now I don't have A1 or A2. That's not what I measured. I'm down here. Well, okay, let's say I'm up here, and I'm observing this with my telescope. I'm not observing a distance. I'm observing an angle. So this is alpha 1, and this one is alpha 2, where A1, the semi-major axis of the smaller one, is going to be the distance times alpha 1, and A2 is going to be the distance to the thing times alpha 2. Everybody good so far? So this is just the angular size. Alpha 2 is just the angular size of the orbit of one of the stars. So I take that. Now what I actually see, so this isn't really true. What I actually see is A2 times cosine of the inclination angle, which we're calling I. Why is that? Because what I see, if this is the orbit, and this is the inclination angle. The inclination angle is measured relative to the angular momentum vector of the orbit. So if this is me, the angular size that I see is going to depend on the orientation of the orbit, like cosine of theta. So if my orbit is like this, then the angle that I see is the semi-major axis. But if it's at an angle, what I see is the projection of the semi-major axis, which is a1 times cosine of theta. Does that make sense? That's where this cosine theta is coming from.
Would it also be sine alpha, or are you just like using?
No, don't think about theta. Don't think about alpha yet. Just so we're all in the small angle approximation. So alpha is always small. So sine alpha is just alpha.
And are alpha 1 and alpha 2 switched on the picture? Or should it be 2
Oh,
corresponds? Yeah, I was just making sure.
Yeah. You want to make things consistent. So I rearranged this to get alphas, because alpha is the thing that I can measure. A is not a thing I can measure. I can't go out to Proxima Centauri and get a tape measure and measure the distance between Proxima Centauri and Alpha Centauri. I can't do that. I don't have a tape measure that long, because that's like 10,000 light years. No, not that much. It's like a tenth of a parsec. So like a fraction of a light year. So I need angles. So we just solved this for the angle. I put an angle in here, and I'm left with m1 plus m2 equals 4 pi squared over g, which I don't really care about. And then I'm just going to get those things into here. We're left with d over cosine I cubed. That comes from this. And then alpha 1 plus alpha 2 cubed over the period squared. And the period's the same for both of them.
What is I? Sorry.
I is the inclination angle. It's the angle between the angular momentum vector of the system and the observer. So this is how you get masses from a visual binary. Alpha 1 and alpha 2 are things I can measure. D, hopefully I can measure that with parallax. So if I can measure D with parallax, alpha 1 and alpha 2 I measure with my telescope, and P I measure with a clock, then I get the sum of the masses of the stars. This is very valuable. So that's the first bit. So the second bit, if I have a spectroscopic binary, so for visual binaries, it's really best if the inclination angle is, if the orbit is face on, because then you can see it better, right? You can see the distance. But for a spectroscopic binary, it's better if the inclination angle is 90 degrees, because then you're seeing the velocity. You don't need to see the angular separation as much. You need to see the velocity of the objects. So, if you assume the orbits are roughly spherical, then the velocity of the first star is just going to be a1, its orbital radius, divided by its period. So 2 pi a1 is the circumference of the orbit divided by the period. Sorry, I totally forgot one of the steps and how these things make sense. Now I got it. So I know that R1 equals mu over M1 times R, and R2 equals mu over M2. Actually, let's do it the other way. Let's use the other equation. Don't use that. M1 over M, and R2 is minus M2 over M, R. So I can see that M1 is going to be proportional to A1, and M2 is going to be proportional to A2. Oops, sorry, one over. Because of this relationship.
And are those over big M, the total mass?
Yeah, that's the total mass M. So I have that M1 over M2 is going to be V2 over V1. So the velocities are going to be reciprocally related to each other. But this isn't this is the velocity of the object, not the velocity that I can measure. What I can measure is the radial velocity, which is v2r over sine I. So if my thing is going in this direction, this component, if this has a velocity v, then this component is v sine I. This is Vr. Vr is v sine I. Vr is what I can measure. So that's the radial velocity that I can measure using Doppler shift. So then m1 over m2 is going to be v2 over sine v2 radius over sine I over v1 radial over sine I. Hey, the signs cancel. So that's pretty nice. So we take this and we plug it into Kepler's again, and we're left with m1 plus m2. This is the same stuff that we had before. P over 2 pi g v1r plus v2r cubed over sine cubed I. So this is just the same as Kepler's, except instead of A, we've got the velocity. And so that changes how the P, that's where the P, that's why my P is upstairs now. So now I have this relationship for the sum of the masses versus the velocities.
Does that say sine squared I?
It's sine cubed I.
Sine-
Sorry, my parentheses are a little off. It's velocities cubed over sine cubed. You can rearrange this for the mass, and you get this mass function that's kind of horrible. m2 cubed over m1 plus m2 squared is 1 over sine cubed I times p over 2 pi g. I don't care about 2 pi g. v1r cubed. Is there anything that I care about this? So one of the important things to notice is that when you're trying to measure masses, there's a little bit of degeneracy because you can't get an individual mass directly. You've got to do a little bit of trickery. What you get is the sums of the masses. But that's not a big deal. You can work that out with algebra. Okay. Visual binaries use the velocity. So that's good for spectroscopic binaries, and it helps if they're eclipsing. So that's useful for spectroscopic binaries. A special kind of spectroscopic binary. A spectroscopic binary just means that the velocity is coming at you, so that you can see the Doppler shift of this spectrum. Now, if the inclination angle is 0, you can't see that, so that's not a spectroscopic binary. So a spectroscopic binary has the stars kind of coming at you. Now, when the stars are coming really at you, and you have this scenario where the star can pass in front of the other star, then we have an eclipsing binary. And these are very useful because they have these very specific light curves. So we have several scenarios. So let's say that I'm over here. So here's me. And I'm looking at, I got a big star and a little star. So if the big star is in front of the little star, let's see, each one of these stars has a particular radiative flux. And we're going to say we've got a flux over the larger one, and we've got a flux of the smaller one. And then we have a radius of the larger one, and we have a radius of the smaller one. So the specific flux is sigma t to the 4th. That's the specific flux, not the luminosity. If you want the luminosity, you got to multiply by the area of the star. This is the specific flux. So then the brightness is going to be brightness for the larger one is going to be pi L squared times FL. This is the total brightness that you see off that object. Does that make sense? This is just the area term that I see. And then this is the flux per unit area that comes off the star. And I'll have a B large and a B small, which is the same, pi R small squared F small. So if the large star, now oftentimes the small star is much, much, much brighter than the large star because the large star is a post-main sequence star that got really big and fluffy, and the other one is a little main sequence star that's still killer bright.
And what are BS and BL?
So BS and BL, this is the brightness of the thing. So this is the total light that I see.
And for flux large equal to sigma t to the fourth, is that times some constant, like
No.
that's just.
This is it.
That's it, okay.
This is the specific flux. It's just sigma times t to the fourth.
Okay.
Sigma is the constant.
Yeah.
There's not an area here. I'm dividing out by the area.
Okay, to get the, yeah.
Yeah, to get the flux, I want the specific flux. So I divide by the area of the star to get the specific flux. And then I multiply back by the area because I need to do that, because I need the total brightness. So this is me multiplying back by the total area. Now the reason that I'm doing it with the radius of the star is, it will be clear in a minute. So the total brightness that I see is going to be what? Well, when the little star is behind the big star, what do I see? My total brightness is going to be what? I can't see the small star. This is the brightness for the big star. This is the brightness for the small star. What's my total brightness if I can't see the small star?
The big star.
Yeah, it's just going to be BEL. Right, just B from the large star. Now, so this is scenario 1. Scenario 2, you can see both the stars. B total equals B large plus B small. Right? That's relatively straightforward. 3, this one's a pain in the butt. Why? What do you see? Well, I see, let's look at it face on. So I have FL from the big one and FS from the smaller one. So the flux that the total light that I actually see from the big star is going to be the flux from the big star times the area that I see. The area that I see is pi times r large squared minus pi times r small squared. Because I'm blocking this part of the light from the bigger star. Right? The smaller star is blocking this light. Plus the light from the smaller star. Plus f small times pi r small squared. So I have these three kind of these three brightnesses that are going to be important. And what I see if I look at this as a function of time, so this is the brightness, the total brightness as a function of time. It's going to be B2. We have a couple values. So B2 is the brightest it can get. And then B1 is, B2 is when you can see both of them. B1 is when you can only see the smaller one. B3 is when you can see some of the smaller one and the bigger one. So that's probably here. Let's exaggerate this a little bit. So we'll say that B3 is here and B1 is here. So my light curve looks like this. For the most part, you can see them both until the little one goes behind the big one. No, in front of the big one. And then it comes out, and then the little one goes in front of the big one. And you're left with the curve like that. So this is the brightness that you see. So this top brightness is both of them. The higher minimum is when you can see just the big star, and the lower minimum is when you can see the higher minimum is when you see the big star and the little star. The lower minimum is when you can only see the big star. or perhaps the other way around, depending on the brightness of the two stars.
So B2, the second case, is when they're just either side by side or just like not eclipsing.
Not eclipsing. So side by side for any scenario that is up to and including them touching. As soon as they touch, it's eclipsing now. So how does that look? What does that actually look like? It's going to look like it's going to have some down, and then there's going to be some plateau, depending on how much you see. So what's the width of the darkest part? Let's pretend that this is the only thing giving us light for the moment. It moves back here. It's going to move. The slope of this is going to tell you the radius. So the fall, the time it takes for it to fall, is going to be V equals R times D, right? Sorry, that's not how I should do it. So there's this Pixies song, and they say, anyway, they sing it in a funny way, but they talk about distance equals rate times time. But they say D equals R times T, and that R is distance. So D equals R times T, where R is the rate. Let's call this a velocity. So the time it takes for this to fall down is going to be the radius over its velocity. Does that make sense? So I can figure out this rise time. The time it stays really dark is going to be the radius of the large star divided by the velocity. Does that make sense? And you can sort out the orbital parameters of the two objects based on this geometry. And you can sort out the ratio of the temperatures. So you can do a little bit of algebra, and you can look at this limit, and this limit, and this limit. So the three of these give you three different brightnesses. And we'll call this one the BP. This is the primary minimum, and the BS is the secondary minimum. So you take this, so we would call this one would be BP, and this one would be BS. Because this is the primary minimum and this is the secondary minimum. It's a little brighter because you can see the little star as well. You just do a little bit of algebra and you're left with this kind of gnarly equation. B naught, let's call that B naught, minus BP over B naught minus B S is just the ratio of the fluxes, F S over F L. Now, because the flux is just, this is just a constant, right? So that's just related to the temperatures, S to the fourth over TL to the fourth. So here's this cool thing. You watch one star go in front of another star, and out of that you can get the ratio of their temperatures, just by looking at how bright things get. So this equation, I didn't do all the algebra to get to this equation, but that's straightforward. It just comes out of these. Does this make sense, or do these make sense? Does anybody have any questions on?
So now there's two BS's though, because there's B small and B secondary.
Oh,
So
yeah.
could we just write that as B3 for B secondary?
Yeah.
Since that's what it is.
That's called, okay, so let me do it. So this is what they call it in the book. Let's call it B1, B2, and B3. That'll be B2 minus B1 over B2 minus B3. Thank you, that does make things make more sense. So that's how you can get temperature ratios from eclipsing binaries. So what else can you get from eclipsing binaries? All kinds of stuff. You can see the radius of both. You can see the radius of both stars if you can get the mass. Yeah.
What about, does limb darkening do anything to the flux, like the graph, the overall graph?
Oh, the graph here? Yeah, but this graph, the way I drew it here is shitty, so you can't actually see where the effects are. So yes, it does. So when you're actually doing this properly, you have to take into account the shape of the star. But we'll talk about that in a little bit. Okay, that's all I have to say about binaries. Binaries are very fun. I'm going to make you do some homeworks on them, and they'll make more sense once done that. Okay. Great. I got 20 minutes to do this super confusing stuff. Okay, now we're going to start with radiative transfer and opacities. Where are we at? So I have this quantity, energy. And I feel like I understand it. 1/2 mv squared, or sigma t to the 4th, or kt. So I have a certain amount of energy coming out of a thing, wherever that thing is. So for me, that is the nuclear burning in the center of the star. That energy wanders its way around to the surface of the star, and then comes out and then runs into the fluffy little clouds in the atmosphere. They're not, sometimes they're fluffy little clouds. Sometimes they're big archy things. So there's the atmosphere in the way, and then there's empty space, and then there's me. So,
Sorry.
yeah.
Quick question. What is the difference between the photosphere and atmosphere of the star? Is it the same thing?
The atmosphere is everything that's above the surface, and the photosphere is just one part of it. And I don't remember the structure of the stellar atmosphere off the top of my head, though I should. I'm teaching in class.
Isn't it the second layer and the chromosphere is above that?
Yeah, I think the photosphere is the closest layer, and the chromosphere is the next layer out
So that's the atmosphere of the star?
of a star, yeah. But I think, in general, we're just talking about all of the gas, all of it. So what happens to the light? After it leaves this point, so there's nuclear burning, and then there's a random walk out to the surface, and then after it hits the surface, then it can mostly freely stream, but what happens is it gets blocked by the stuff in the way. So if you think about just a stream of things. I start off with a certain density of things. These are photons, so I have a density of photons in ergs per volume. Let's talk about ergs per volume for a second. This isn't the thing that we'll talk about a ton. This is an energy density. We do talk about an energy density in a second. But I is the energy density in this stream of photons. It starts off here, and it's at its fullest, where it is being radiated by the surface of the sun. So the surface of the sun is 6,000 Kelvin. It is giving us a beautiful black body at 6,000 Kelvin. So the light that comes off of that, I naught, is going to be my sigma t to the 4th. That's my total light. Well, that's the total light from the star. So I need to actually break this. So I need to break E into a bunch of bins, because this has too many things in it. I need to break E into its wavelength and the area of the star and the direction of the photon. This is that solid angle thing that you guys got confused about. I don't know, by you guys I mean everybody. Everybody gets confused by that. So my light starts off here at sigma t to the 4th. Or maybe I'm looking at a black body. Maybe I'm not looking at the total luminosity. I'm just looking at a black body times 4 pi squared r squared. That's my total light coming off. Well, now we need to divide by the surface. So we just want to think about a specific. By specific, I mean we've divided out all the extrinsic quantities. Oh crap, extrinsic versus intrinsic. Have you guys talked about extrinsic versus intrinsic in any quantity? I have never heard the word extrinsic before. I could use to hear it a little bit more about it. There you go. Okay, let's back up a sec. let's take an aside right here. Actually, let's do it on this board. I don't need this stuff anymore. So, this is something that you'll belabor in StatMech a little bit. So we have two kinds of properties, extrinsic properties and intrinsic properties. So an extrinsic property depends on how much stuff there is. So it's proportional to the mass, or the total volume, or the total whatever. An intrinsic property is not proportional to how much stuff you have. So velocity is the velocity of a car an intrinsic property or an extrinsic property? Intrinsic. If I have two cars and they're going at 40 miles an hour, still going at 40 miles an hour. It's an intrinsic property. What about the mass of the car? That is extrinsic. It's proportional to the mass, being the mass. What about the volume of the car? That is extrinsic. The color of the car? It would be intrinsic, because it doesn't matter how big the car is, the color stays the same. I can make my car huge, and the color stays the same. The mass might go up, the momentum might go up. What about the fuel economy? Is that an extrinsic property? Or, that's an extrinsic quantity, because that depends on how heavy the car is. So we have two ways of thinking about things. And as physicists, a lot of times what we care about is the extrinsic property. I need to know how many photons are coming off of the sun per unit of time. I want the total number of photons. But that depends on how big the star is. And then I've got all of these factors of the masses of all my various stars kicking around, and that's a headache. I want to divide through all that so that I can talk about just what happens to a stream of photons as they come out. And then I'll multiply back by the mass of the star to get the actual spectrum. So a lot of these, so that whole first 9.1 is just kind of switching between the intrinsic quantity and some various extrinsic quantities that we have averaged out. So the intrinsic property is not sigma t to the fourth. It's I, which is in energy per wavelength per area per solid angle.
And that's the intrinsic, you said?
That's the intrinsic light. And that's really what we care about. So what the book does is then goes and averages this a couple of different ways. We can average over the solid angle, so saying we don't really care about which direction the photons are going in. Sometimes you do and sometimes you don't. So we can average over that and we'll get the flux. We can average over the energy to get the mean energy, and that's really just a units change. But there's a couple of different ways we can take averages of this quantity, which is basically the very most intrinsic of the ways to describe my stream of photons. Does that make sense? So I've got light. We just want to talk about light, not the star below it, not what's making the light, just the light. So now I've got I, which comes off my star, and then propagates through this field. Think about this think about this like a density of photons for a minute. What happens to the density of photons as my packet of photons goes through this atmosphere? What's going to happen to my photons?
Some of them are solid.
Some of them are going to get scattered, absorbed. Those are the only two things that you can do to a photon. You can't do anything else. You can scatter it or you can absorb it. You can either change its direction or change its energy or, consume it completely. So some of those photons are going to leave. So as I go from this point to this point, we're going to talk about di. This is what's the change in I. How much does I change from one point to another? Well, I've got some fraction of those. Some fraction of my photons are going to leave. That fraction, so I can write down a differential equation. We'll say di ds, so this is how much intensity I lose for a little bit of path length. this is just gonna be, and so it's gotta be negative, right? Because the number of photons is going down. And it's gotta be, I'm losing a fraction. So it's gotta be proportional to the number of photons that I have initially. So this is gonna be kappa times I. And I need a rho in here because I need the density of the stuff. So kappa is the opacity, and this defines how many photons I'm losing out of my stream. And rho is the mass density, because we've gotten rid of the density. The density doesn't matter. This is only, kappa only depends on the microphysics of the particle. So what's going to change? So why do I lose particle? Why do I lose photons? So I have, this is now a totally zoomed in view. Now these are all H atoms, hydrogen atoms. I have a bunch of photons coming in. I'm going to lose more photons if I have more hydrogen atoms. So if the density goes up, I'm going to lose photons. If I change the electron structure of the hydrogen, I'm going to change how I lose things as well. So kappa is the opacity. Nu. And it's the fraction of photon density I lose along the way.
So is it total or is it dependent on time?
Which?
The kappa.
Kappa only cares about the atom. It doesn't depend on time at all. So kappa is kind of as intrinsic as we can get. We've gotten rid of all of the other things about the environment that might change things. Kappa only depends on the relative cross-section of this to a photon.
So kappa is the value, like, is it unique to the star or is it?
No, it's unique to the atom.
Oh, the like opacity of the atom.
Yeah.
Oh.
That's why we divide through everything. That's why I'm talking about all this intrinsic. The star is gone.
So it doesn't matter how much gas there is in
A
the
little bit. It matters how much gas there is by way of the density. So the density of gas matters. So rho is just the density of gas. Rho is just in grams per cubic centimeter. That's just the mass density. And then kappa is what fraction of whatever mass I have. For one atom, how many photons am I going to lose? Yeah.
Are you multiplying by rho there? Is that
Yes.
K over? Okay.
Let me write that a little more clear. This is kappa of nu times rho times I nu. This is the radiative transfer equation. So one of the important things is understanding what kappa is, because this tells me how my energy source depends on the crap that it goes through. So I can solve this equation, right? So this is a differential equation that you should be able to solve just by looking at it. Your brain, by the time you're done with your physics education, will solve this automatically for you, and we'll just kick it in. So if I have df dx equals AF, F equals what? This is a differential equation that you should just ingrain in your head. Can everybody do that?
Is it e to the AF?
Yeah, this is e to the AF. So now I don't mean to be judgy here. This is why I'm putting it up and talking about it. This is something that I want everybody to stare at and think about and have a relationship with this differential equation, because it is one of the most important differential equations that there is. If I have something whose derivative is proportional to itself, I get an exponential out of that. So I can solve this equation because kappa is going to be independent of position. Kappa is independent of position because it's independent of everything other than the structure of a hydrogen atom or a dust particle or a helium atom.
And what is S?
S is distance. So what I'm doing is so there's a star over here, and we divide out all the characteristics of the star, its size and its mass and all that stuff. And we're just thinking about the fraction of photons. So my light starts here and then decays like that until it gets to the end of the cloud. So I have a star, I have some path, this is S, and this is I. I have some path through my cloud of gas, and photons are getting kicked out as I go along, and they're going to decay in an exponential way. So I can write this equation, I of S equals I naught. This is let's call this I1. This isn't something specific. This is whatever the star is doing at its surface. Times e to the minus kappa times S.
What is S again?
S is path length. It's distance.
And is I1 the initial?
Yeah, this is the initial. So this is what came off the star.
Is that different from I naught over there?
Yeah, it's the same as I naught over there.
Oh.
But there are several things like L naught that are specific numbers. This isn't a specific number. This is whatever the star is doing. And then you got to decay that light by e to the minus kappa S, where S is how far through the cloud you've gone. Does that make sense? Where am I? I got 2 more minutes. I wound up just jumping straight to the beat rather than going through my notes in careful order the way I wrote them out.
What is in the exponent again? Is that
Kappa times S. Oh, sorry. I wrote that like a little. That's the wrong S. Let's see. Other things that I want. See, radiation pressure is important. We'll talk about radiation pressure again later. Is there anything? I got 2 minutes left. Oh, I got 1 minute left. Is there anything really crucial? So, yeah, the last thing I want to talk about is mean free path. So I want to talk about mean free path real quick because I actually intended to talk about it beforehand, but I forgot. So when I have a collection of particles and I have another particle, maybe it's the same, maybe it's different, that's going to go through these particles, how far can I go before I run into one? The answer is, well, if I think about making a cylinder, and we're going to look for the length of this cylinder before I can run into something. So how many things are in my cylinder? My cylinder has a volume of sigma, which is the cross section of the atom, times L, which is how far it goes. And this has got to equal 1 over the density of the particles. So if the density goes down, this goes up. So, or you can say that the mean free path is 1 over sigma times n, where sigma is the cross section. And that's like, how big is it if you're going to hit it? So this is a difficult thing to compute. And you'll spend a lot of time in quantum mechanics thinking about cross sections. The cross section of a hydrogen atom is kind of like an angstrom squared. So the Bohr radius is the size of the hydrogen atom. The cross section sigma is kind of like pi times the Bohr radius squared. But not really. What is it for a free electron? It's actually way bigger for a free electron because a free electron interacts with the electromagnetic force, which falls off really far. So the cross section is very difficult to compute or really think too much about. You think about it like just the area that the thing subtends. So it's just how much area the thing matters.
Is it like its interactive radius? Like
It's
how
the
far it can
interaction
interact?
radius. Yeah, it's really the interaction radius. So if you have a baseball,
Is n number of
to have a
particles-
baseball, the cross section of a baseball is pretty clearly defined, right? The cross section of something that has electromagnetic fields in it It's harder to define, but you can still define it. You just say, what's the probability of scattering based on hitting it? So that's something that you'll do in quantum mechanics.
Is n number of particles there?
Particle density. So the number density of particles. So this mean free path is something that we use all the time because it's kind of gives you a measure of not just how dense it is, but also how big are the particles. This cross section is the same as kappa. So kappa is the cross section times the mass of the particle. No, divided by the mass of the particle. So kappa is just how big are the particles. Now that means different things, okay? So how big is a hydrogen atom in the ground state if you are a radio photon? What's the probability if you've got one hydrogen atom in the ground state? What's the probability of a very low energy radio photon interacting with that atom?
0.
0. It can't. So the cross section is 0. What about if you're a photon with 13.6 electron volts? You're going to ionize that thing. So that photon can hit that atom and ionize it. That cross section is much larger, slightly less than 13.6 electron volts. Way different cross section because now you're going to do different things. So cross section is complicated because it not only depends on the thing. So the cross section of the baseball is pretty fixed. It doesn't depend on the batter. But if you're a photon, the cross section depends on the batter. Okay, that's all I'm going to say for today.
Like your wavelength has to match the thing you're trying to interact with. You cannot see something if your wavelength is bigger than the thing you're trying to see, right?
Yes.